I thought you already.
All right. All right. Hey, everyone. How's it going? My name is Justin. I'm Nader's PhD student. Nader unfortunately can't make it today, so I'm going to be subbing in for him. I believe it is presentation module T4. Is that transient execution defenses? Awesome. Great. So that's a really interesting area. I'm excited to see what you guys have presented. I have the presentation list here. Just can you raise your hand if you're presenting today? Okay, cool. So let's go ahead and get the schedule up. And what we'll do, as we've probably done in prior times, is if you're presenting, if you can bring your computer up and join the Zoom link here, then you can share your screen over Zoom, and then you're good to go. Let's see. So T4 is Pierce, Chong, Alp, Inigo, and Matthew's group here. Yeah, do you guys want to join the Zoom? And then you can come up here. There's a passcode. Here, let me find that for you. Let me see if I can. Ooh, that's not good. Is this my? Is there? Where is it usually at? Just copy it. Oh, here it is.
Oh, there.
482-139.
I'm doing.
482-139. And then once you're in, I'll let you in.
I'll share my.
This morning I was faxing with the 20% goddamn simulations. Don't. Yeah.
All right, and I have recording going, so we should be good to go. Yep, here I can. And how long does Nader say you have to present?
About 10 minutes.
About 10 minutes? Okay. Yeah, go ahead to get started when you're ready.
Hello everyone, we're going to be presenting of speculative constant time by compilation. My name is Al.
I'm Pierce. I'm Matthew. So let's start with some background on a key concept that is talked about in this paper a lot, which is speculative constant time. Considering this code over here, we have some private data in stack A, public data in stack B. We have some kind of bounce check, a load, and a branch on condition y equals to 0. So this program is something cryptographers call constant time, because the time taken to run this program is not dependent on the private data. But however, if the CPU does some kind of speculation on the branch, it might execute some code that accesses A when it's not supposed to. So this makes it not speculative constant time. And this might open up vulnerabilities against like transient execution attacks. So one way of defending against this is using a technique called selective speculative load hardening. And basically this is like a way of annotating the code in such a way that secret data does not get exposed when speculation happens. And some of the annotations include like speculation flags and a protect function that you can add to the code. So the problem that the paper is trying to address is a lack of formal guarantees that speculative constant time is preserved after compilation. So techniques like selective SLH exist at the source code level, but there is no formal proof that compilers preserve them after compilation. So an example of a code that is given in the paper is on the left here. That you can see that it's speculative constant time because within it there are some annotations that use speculative load hardening. But after compilation with GCC at optimization level 1, the compiled assembly language code is not speculative constant time because there is no protect flag or miscalculation flag in there. So the proposed solution that the authors came up with is to formally design and verify a proof of concept compiler that maintains SCT properties. So they do this by proving the compiler within a framework that can be seen in this, it's encoded in this commutative simulation diagram on the left here. And this basically shows something they call backward lockstep. And basically how this works is that there's a initial state for both the source and target program. And the target program takes a series of steps determined by a directive D to reach the next state T prime. And while taking this series of steps, it emits some kind of a side channel observation denoted by OT. And because the program T is compiled from S, we can say that S can also take a series of steps. There's a function of dt called gdt over there to reach the next state S prime. And while doing so, it also emits some kind of side channel observation OS. And what the authors want to prove is that OT is a function of OS. And basically the key idea is if the compiled program leaks something under speculation, then there must be some kind of matching source execution that leaks the same. So this means that the compiled code is no more leaky than the source code.
For evaluation, the authors of the paper were actually able to prove that their simplified compiler preserves speculative constant time. And they're able to do so by showing that the 9 standard passes used by their compiler, each of them preserve speculative constant time. And the way they actually prove this for each of the steps is actually use COQ through persistent, which allowed them to describe each of the steps of the compiler formally in formal logic. And this allowed automatic verification of that each of the steps preserved SCT. As for the actual applications that they evaluated, they mainly looked at Jasmine, which is software focused, which is a programming language focused on being able to have hardware security for cryptographic software, and specifically the libjade library. The Jasmine framework's implementations of SHA-3 and MLChem were tested against the revised SCT system. And most programs in libjade actually passed the speculative constant time checks without any modification. As for the main results, the results in my interpretation are actually very impressive because they're not only able to come up with a verified formal proof that they were preserving speculative constant time, but their results were also shown to be practical for applications in Jasmine and specifically libjade. Furthermore, they were able to show that these changes can be made with very minimal code changes. And actually the performance penalties of these changes were often less than 1% of the slowdown. And this is a much more efficient solution than other solutions to problems like for specter attacks, such as fencing, which are frequent fencing, or even the other security measures really decrease the performance by much more.
So in conclusion, this paper addresses that constant time alone is insufficient against speculative execution attacks, which includes Spectre V1. And they also introduce a formally verified compilation strategy that preserves SCT, as discussed by peers. And it highlights that the compiler optimizations can invalidate source level protections unless they are rigorously analyzed and tested. It also defines a core language, as Matthew touched upon, the semantics, as well as a suite of compiler passes, which are all proven to be SCT observing. And for instance, libjade and Jasmine, it demonstrates a cryptographic code, which can be secured with negligible overhead around 1%. So what type of future work could be implemented? So the SCP preservation to other spectral classes, including V2 or V4, and including other types of transient execution attacks, would be a good step forward, as well as integrating SCT-aware passes into compilers such as LLVM and GCC. Developing less restrictive SCT systems to ensure safety under speculative semantics, as well as embedding SCT checking mechanisms into real-world cryptographic development pipelines. And this is more in line with Nader's idea of secure code development, such as using Rust, etc. And it also improves error reporting and developer guidance in SCT type systems for better adaptability. And we have 3 discussion points. So if anyone wants to have a go at it, how can we ensure secure by construction software development when compiler optimizations can introduce speculative execution vulnerability?
That's just general, but I think this motivates using private compilers over his open source. For instance, now a bunch of open sources will have access to the microarchitectural code to implement.
So yes, and what we assume through this paper is that we can redefine the compiler as part of a trusted computing base and ensure secure by construction development through formally verifying each compiler processes speculative time constant. So this way, through the development stage, we can ensure that our secure compiler can also be secure for software development. Our next question is, given the high complexity of formal verification, how can we scale such guarantees to the mainstream, including compilers like LLVM or GCC without compromising maintainability? Okay, so this is so we can implement verified backends for security critical code paths, utilize cryptography to isolate integration burden while still interfacing with larger unverified systems. And then our last discussion point is what kind of balance can we have between offering developers the power, low-level languages, and enforcing restrictive security disciplines like SCT that may interfere performance and or usability over it. So as Pierce discussed, a system like SLH, which is selective speculative load hardening, allows developers to write low-level code while still ensuring SCT compliance with minimal performance. And thank you for listening to us.
All right, thank you guys. All right, let's see. So next presentation is Yujia and Pejun here. You guys. All right, and then why don't you guys have Zoom open?
Oh yeah.
And then the meeting code and password are right behind you.
Need to be allowed to read.
Oh, here. Yeah, here we go. All right. That's good. And then you can stay unmuted, or sorry, muted. And then you can share your screen. All right. Yeah, also the mic is gonna be here, so when you present, you can like stand here.
Okay.
But you can like switch sides if you want.
Okay.
Yeah. Great. And feel free to get started when you're ready.
Okay. Okay, so hello everyone. Today we're gonna talk about the Libra, which is kind of the architectural support for principled, secure, and efficient balance execution on high-end processors. So first of all, let's take a look about the question today. So in this paper, the authors announced the kind of question that how can the secret dependence control flow be securely balanced on high-end processors without increasing the high performance cost of full linearization? And to know these problems, we need to see some background related to that. So from lecture 4 and 5, we can know that modern CPUs can also leak secrets without with the control flow, not only through data access. So instruction cache, branch predictors, and other things can also expose data dependence execution paths. And this can be used by the set channel attack, especially for the control flow leakage attack we're gonna talk about today. So the CFL attack will focus on monitoring the control flow to reveal some sensitive information, such as the secret data or program behavior. And to counter those attackers, there are currently two main methods. The first one is talk about the linearization of secret dependence control flow. And this is aligned with the constant time techniques discussed in class before. And this method defines the attacker by eliminating all the secret-related branches. And since there's no more secret to be observed, the CFL attacker cannot implement the attack. However, it will make the program become really hard to maintain because it just eliminates all the branches, and the cost will also be really high. Another method will be called the balancing secret dependence branches. And this can generate less overhead because it's just to try to make every execution of possible target of control transfer instructions looks the same to the attacker. However, it's only proved to be safe in some low-end processors. This is because nowadays the high-end processors all have some critical performance enhancing hardware. So when these hardware being shared by different security domains, the dependence of the data information can be leaked to some in an unbalanced way. In other words, this unbalanced leakage will break the equilibrium made by this method. And although both of these two methods seems to be useful in counter some side channel attack, however, the fact that the unreliability of the second method made the first one become a kind of the industrial standards. Like the people call that the only effective countermeasure. But is that true? This is the question the papers make. Against this background, the authors of this paper decided to propose a new way of thinking about the counter those attacks based on leakage, especially to the control flow leakage attack. And this method is called Libra.
Instead of eliminating secret branches, Libra asks a different question. Can we return secret-dependent control flow and still be secure? The key idea is to allow secret-dependent branches, but make sure that both paths are indistinguishable from the outside. To achieve this, Libra introduces the concept of folded code regions. When the program encounters a branch that depends on secret data, Libra will take the instructions from both branches. One is true branch and another is the false branch, and interleaves them in memory. Regardless of whether the secret is 0 or 1, the CPU fetches all the instructions in the same order, just like this in a line. This ensures that microarchitectural behaviors are identical across both branches. At runtime, the CPU uses the secret to decide which instruction to actually execute. The other instruction is skipped, but still fetched, which means its object is touched, but its logic is not wrong. The key is that any attacker monitoring the instruction cache or timing behavior will see the same pattern regardless of which path was taken. To support this execution model, Libra introduces a new instruction to the ISA, which is level offset branch. By using this instruction, the CPU will enter a folded secret dependent region. Then the processor will switch into a special execution mode. In this mode, the program counter will no longer reveal which instruction within the folded region is being executed, only which level or group of instructions is active. As you can see, in Libra, each pair of instructions from a secret dependent branch is grouped into a unit called a slice. For example, slice 1 contains A1, B1, slice 2 contains A2, B2, slice 3 contains A3, B3, where A is from the true branch and B is from the false branch. So even if the actual program counter points to A1 or B1, the attacker cannot distinguish them because they both map to slice 1 from an external view. The CPU prefetches all slices of the region in a fixed order, so there's no variation based on the secret path. Therefore, behaviors of those performance critical components will no longer leak secret information. Let's look at what Libra contributes and why it matters. The big idea is that Libra challenges the old belief that secret dependent branches are always unsafe. Instead of removing them, Libra shows that we can still keep those branches securely with the right hardware support. To make this happen, the authors introduced a clear contract between hardware and software, so both sides know what to guarantee. With the minimal hardware level changes, it achieves the classification of leakage source. Finally, they built Libra on a RISC-V chip and show that it runs about 19.3% faster than current constant time linearization method. So in the end, Libra gives us strong protection with acceptable cost.
Okay, I'll introduce you how they evaluate the Libra. As mentioned before, all experiments were run on the FPGA of the out-of-order RISC-V core, and they run 11 test benchmarks, and for each benchmark, they run the test on 4 groups. One is a baseline with no side channel defenses, and a software transformation, and a fully linearized code, and a Libra folded version. And they basically test 4 metrics. First, the execution cycles to quantify the performance and speed. And another one is binary size to measure the code inference and the synthesis error, and the security validation to confirm that their code has 0 leakage of secret inputs. Here's a summary of the results. We can see that the Libra coded version has better performance than the conventional method, which is linearized code. And we can also see that the Libra is lightweight, and from the hardware perspective, Libra support cost 10% more LUTs and registers, which is acceptable for the small hardware workloads. And finally, for the security test, the RTL non-interference test has verified that Libra is fully secure. And for the future works, so inspired by the works, we can see some promising directions. So first, there is no branch prediction for Libra right now. So there is a small QQ3 cycle penalty store for them. And for the deeper pipeline, the penalty is much larger. The future work could be planning to explore the speculative slash prefetch and branch reservation for the Libra structure. And the second, there is no compiler support for them. There is a limited scale of evaluation and a higher risk of human error. So how to express the contracts that can be consumed by the compiler is also one future direction. And what's more, they can also extend their contracts to cover more microarchitecture structures, and maybe they can also generate the leakage contract from the hardware description, like the RTL level.
And for the sake of time, maybe you want to ask one question from the discussion?
Okay.
Yeah.
Okay, so let's take this first one maybe. So beyond the control leakage, what other types of microarchitecture leakages are difficult to mitigate purely through the software? And could a contract-based co-design approach like Libra's help address them? Is anyone interested in this question? Or the second one, what challenges might arise when deploying Libra in real-world systems? And how can we balance security and performance? Does anyone have ideas from this too? Okay.
So if not, we have some basically ideas through these two. So um, so for the first one, I think like other micro leakages are hard. It's because some timing variations are hard to execute. So because something depends on the hardware internals, so software cannot control them or like observe them. However, something like the Libra can use another way to help them to control. So in this, we know that it's just create like two channels and combine them together to be one. So in this way, it can just prevent outside of observer to observe them. Yeah, thank you guys.
Next up is Valerie, Li Feng, and Cody here. All right, do you have the Zoom?
But I don't know why it said the code is invalid.
Okay, 977-5948 and 5982.
Oh, yeah.
Okay,
Oh,
and then 482139. All right, I'll let you in. Then you can stay muted, and then when you're speaking, you can speak muted.
share my screen.
Yeah, and share your screen. There you go.
Hello everyone. My name is Valerie Wang, and this is Bifo Mei, and this is Cody Ding. And today we are going to present P4.3 Phantom Trials, the practical pre-silicon discovery of transient data leaks. And here's the outline of our presentation. So let's start with the research problem. So the current founders for transient vulnerabilities address problem of navigating the huge search space by employing templating. The first one is breaking up known end-to-end attacks into individual stages that serve as a blueprint for creating new variants. The second template is providing the further with program snippets such as try to access a secret or slow down an instruction to mimic the behavior of known POCs. However, the problem for the bias further towards known issue will causing overfitting problem. So the current fathers need restrictions like templates because their underlying detection models overly constrain the space of programs that can trigger a violation. So the first one is current detection models rely on explicitly defined secrets. And second problem is the current fathers only detect violations after a secret is transmitted through a covert channel. It will requiring full end-to-end attacks. So for the background information, the transient execution attacks have three phases. The first phase is priming step. The second one is secret access step, and third one is transmission step. For the classification of the attacks, the first one is a meltdown-like attacks. The attacker access data belonging to a different security domain through a faulting instruction. And the second class is a Spectre-like attacks. The access occurs in the same security domain by a victim acting as a focused deputy while the transient window is generated through speculation. The covert channel is in transmission step. It transmits the secret via a timing covert channel. So the figure on the right shows the phases of a typical Spectre attack including flush and reload. The attacker first primes the microarchitecture by flushing the cache 1, and then forces the victim to transiently access a secret 2, the value of which gets encoded in the microarchitectural state, which leaks to the attacker by means of subsequent time loop 3. And for the existing detection models, the existing detection models are all in the pre-silicon fathers. The first one, the introspector defines a set of gadgets, that is snippets of code taken from known vulnerabilities and combines them. And spec doctor use template-based multi-phase fuzzing to uncover end-to-end leakage via covert channels. So for the secret tracking, the introspector fills memory with known secret values and detects leaks if they appear in microarchitectural buffers. Spec doctor use the differential testing by running a program twice with different secret values and checking for changes in the microarchitectural state hash. And STT and cell IFT use hardware information flow tracking to precisely monitor secret data flows, though not in a fuzzing context. So for the secret definition, STT is a microarchitectural defense that treats speculatively accessed data as secret until the instruction faces a point of no return in the ROB. And cell IFT and spec doctor use a predefined secret memory region isolated with hardware primitives like PMP and or page flags. And the introspector also use page flags to identify secrets, allowing them to evolve with permission changes made by gadgets.
So unlike traditional solutions, Phantom Trails focus on transient data leaks. It does not wait for a full side channel chain to complete, which means the moment secret data moves from memory into any sensitive CPU buffers, such as the register file, it is considered as a vulnerability. So you don't have to model or wait for a cache timing probe or any other covert channel. And you can catch the root cause, which is speculative access rather than its side effect. No, it's okay. No. And conventional approaches rely on explicit secret, meaning you must mark specific address ranges as secret, which limits the scope of detection, while Phantom Trails instead uses implicit secrets. Means you automatically treat any data the program never legitimately accesses as secret, thereby catching a far broader class of leaks. We can also classify types of vulnerability. So when taint appears in the buffer, Phantom Trails does not immediately crash the simulation. Instead, it waits for the CPU's next flush signal. Because the type of flush signal let us determine which class of vulnerability has been triggered. For example, a branch misprediction refers to a spectral V1, V2. An exception points to a meltdown, etc. And how do we actually do that? Here's a diagram of the overall structure. The basic idea is that they use an ISA simulator, in this case, Spike, to generate some sequence of instructions. It will also record every memory that program will actually touch. Then all other addresses in the DRAM will be marked as tanked, which is the idea of implicit secret I have talked about. Then we can compile the RTL code through Verilator into a cycle-accurate simulator. During the cycle-accurate run, we watch for tanked flowing from DRAM into the register file. So the moment tainted value reaches the register file, we immediately raises transient data leak alert.
So for the evaluation methodology, the random choice tests on the Chrome RISC-V CPU and both medium core and large core. And the random trial is evaluate to evaluate if it can detect different types of vulnerability, and also it was compared to the other browser like SpecDoctor, which mentioned in the previous slide, like compare their performance. And in the paper, the group decided using two types of feedback. The first one is a software feedback, which is for edge coverage, and it will give the group a broad explosion of CPU behavior, and also the continued feedback, which is for the leak detection. And for the main results, the phantom trial actually detect all 5 known vulnerabilities, and it also outperformed the previous browser, both in the prediction quality and speed. And there's still high processing throughput despite adding the taint tracking. And also there's the new types of vulnerability discovered by the group. And for some potential future work, the group want to try to extend their work to x86 macro architecture and internal buffer. They also want to improve their work on hardware, software co-design of fuzzer and detector, and for the real world impact. The actually the boom maintainer actually acknowledged their discovery of the new type vulnerability, which called Spectre LP. And as for the discussion point, so the final trial actually worked well on the boom core, but will it actually scale to more complex core, such as NVIDIA or the AMD? And also kind of work, we extend to detect other types of transient vulnerabilities, such as data assembly attack. And any idea about the questions?
Does this work for multi-core? In a multi-core setup?
Yeah. So my guess is it actually might be hard to scale to the more complex core. And for the second question, I think if it can detect other types of transient vulnerabilities on the boom core, maybe they can try to build up on that, then scale to the more complex core, which I think may need some additional work to scale to the industrial level. And that's all.
I had a question.
Yeah.
You mentioned the Spectre LP bug. Could you expand a little bit more on that? Like, like which, like the setup, like benchmark they use, like what exactly like caused it?
Yeah, so as for the whole spect type, it's like it's caused by the misprediction. And for the LP, I think the full name is a loop detector. So maybe I think it's related to the branch and other stuff. John?
Was it a new benchmark that they tried, or is it one that like other comparisons have been analyzed as
I
well?
think it's like when they're doing the whole work, they accidentally maybe find it. And also the maintainer like acknowledges their discovery, so maybe, yeah, cool.
Awesome, thank you guys. We only have, what was it, 3 minutes? If you want to discuss after, or like, yeah, you need to say, or like, not going to discussion. The other side?
Yeah.
Read the mics here.
Oh, let me stand next to the mic. Okay.
Yeah, I would say I need to go. But you can like switch, yeah.
We can go stand.
Yeah, that's what I'm saying.
Do you want the?
Luckily it's a group too. All right, yeah, I think I let you in, so you can try to share now. Oh yeah, I was just thinking that it's not hard to see. Oh, really?
Wait, I don't think so.
Oh, right.
Perfect. Wait, where?
Oh, there is.
Oh, yeah.
One of them will turn off.
Look at that.
Like different preset
Oh.
modes.
There you go. That's actually perfect.
Yeah.
Thank you.
Beautiful.
All right. Sweet. Okay, ready? All right, hi everyone. I'm Philip. This is Alex, and we're going to be presenting paper T 4.4, which is ghost race exploiting and mitigating speculative race conditions. So for an outline, for those who are watching the recording, we're going to quickly introduce the problem, go over the background, connect it to what we learned in class, and then we're going to go over the author's solutions and contributions, how they evaluated their contributions, the results and insights, and then finally end with some future work and discussion points.
So the main problem statement driving the authors of this paper is how do synchronization primitives like mutexes and spin locks behave during speculative execution? And also, what are the security implications for modern operating systems, especially in an era of Spectre, Meltdown, transit execution attacks?
Yeah, so to first understand better the connection between and security implications between speculative execution attacks and these synchronization primitives, we want to talk first about Spectre v1, which attacks the pattern history table in order to mistrain the branch predictor. This allows us to speculatively bypass the array balance check, and then finally we're able to use a cache side channel attack in order to leak secret information. All data stuff that we already learned in class. So another really important thing about this is what is concurrency. Concurrency is the ability for a system in order to process multiple things, multiple tasks, processes all seemingly at the same time, when in reality it's executing serially. So this also has bugs related with it. In this program, you can see a simple multi-threaded concurrent program. Can anyone see if there's any problems here? Look specifically at the green and the red. You have like 10 seconds. Yes.
I mean, like, you can have 2 threads, and if thread 2 finishes the check to see if the point is or not, before thread 1 actually does the freeing. Basically, if you execute an order, the if statement in thread 2 can free thread thing in thread 2.
Yeah, exactly. Exactly. That's exactly what we're trying to get at. So exactly what she was saying. If we were having to free the memory area, and then now we have the second thread actually running its code, we suddenly have a concurrent use after free attack, in which case an attacker is able to control the flow of the program. And this is very bad because especially we're freeing kernel memory. In this case, we were able to run and execute any arbitrary code. So how do we fix this? Obviously, we're able to just add synchronization primitives like we were talking about earlier in the problem, and this was done in this specific code example using a mutex lock. This gives us a race-free critical region and provides us with architecturally safe code. But then the question becomes, is this micro-architecturally safe code? And obviously the answer is going to be no, which is the whole point of this paper. And another thing we learned in class was how do we prevent all these speculative execution attacks? The easiest way, of course, is to do serialization. This is going to be done through fences. One example, of course, is Intel's L fence, which is prevents loads from happening immediately. So this happens between the rename and dispatch phase, but there's ones that happen earlier in the pipeline, like Intel's M fence and S fence, and newer had things like cache fences and more context-aware fences that we learned about in class previously.
So for the author's proposed contribution, this is divided in 5 main contributions that they outline. The first 3 are about mounting this ghost race attack. The 4th one is analyzing the vulnerability for these SQAF attacks in the Linux kernel. And finally, the 5th one is a defensive mitigation strategy on how we can stop speculative race conditions from being exploited. So just to start on the ghost race attack, what is it? The goal is to exploit speculative race conditions in synchronization primitives to leak kernel data from what is originally architecturally race-free code. So on the right side, we have an NFC device that is being accessed by 2 different threads. And we have 3 main challenges to mount the ghost race attack. First of all, we want to create an unbounded exploitation window between these 2 lines to be able to deploy our use after free exploitation. And the second challenge is that we want to find a way to be able to bypass this mutex right here because it is architecturally race-free. And then finally, we want to combine these 2 to mount an end-to-end attack. So the first contribution is how do we create this unbounded use after free window? Originally, we have an interruptible window of 8 instructions where we can launch this use after free memory leak. And the idea is that the attacker is going to first set a high precision hardware timer that's going to expire during this non-interruptible part. So since it expires right here, the moment we step into this first instruction in the interruptible window, the victim thread is going to be interrupted. And at this point, the attacker thread will coordinate an attack with other simultaneous multi-threads in the system to basically spam the victim thread with inter-process interrupts. So that's the IPI storm that we see on the right side. And the authors were able to show that about 15 simultaneous multi-threads spamming the victim thread with IPIs was enough to create this unbounded use after free window. The third contribution is combined. So actually, we glossed over the second contribution, and that's really just defining the discovery of these speculative race conditions, which are race conditions that occur during transient execution. So combining the knowledge of speculative race conditions with the unbounded use after free window, they were able to mount this speculative concurrent SQAF attack. So this is also the ghost race attack. So steps 1 through 8 are what we discussed earlier, some setup, creating the unbounded use after free window. Step 9, we have the attacker thread, which is going to create a malicious struct with a controlled callback pointer. It's then going to use some slab massaging techniques to place the struct in the exact freed memory location that the victim thread freed in step number 6. Step 11 is going to be, we're going to basically mistrain a branch predictor by acquiring the mutex lock multiple times so that we can speculatively bypass this mutex lock, which relies on a conditional branch, an if statement checking if is it locked or not. And then finally, at this point, the attacker has hijacked the control flow and the attacker control callback function is executed. And the authors were able to create a proof of concept attack that was able to extract kernel memory via a covert Spectre side channel at 12 kilobytes per second. The fourth contribution is the authors were trying to see how widespread this SQAF problem was in the Linux kernel. And so they created this gadget scanner that was looking for these templates of SQAF gadgets. There were 6 of them. They found 1283 SQAF gadgets across the Linux kernel, like the NFC, the near field communication gadget that we saw earlier. So it's a pretty widespread problem. And contribution 5, so at this point, you might think this sounds like more of an attack paper, to which I would agree with you. But the 5th contribution is a defensive one. They talk about some basic mitigation strategies, similar to what we discussed in class. They're trying to place some serializing instructions like an L fence into these synchronization primitives. So it's important to note that synchronization primitives like mutexes are designed to be atomic operations in operating systems, but they're not serial, which means they can be speculatively bypassed. And by explicitly adding this L fence, we stop we force serialization of the synchronization primitive. And so actually the authors of this paper contacted the Linux developers about this. They've acknowledged the issue, but they haven't added this mitigation to the kernel due to performance overhead, which makes sense when we saw Linus's previous comments on SRCs.
Yeah, and exactly like Alex said, even though this is a defense paper with 90% attack stuff, they still it's still mainly a defense paper. So they evaluate both their gadget scanner and their mitigation overhead. So the gadget scanner, like Alex mentioned, is able to find a lot of these different gadgets, mostly mutexes, and then the first and second, the first use and free variants with less than 2 nesting levels. But the main issue with this gadget scanner is that even though it finds 1,000 potential vulnerabilities, there's going to be a lot of false positives, in which case the object is the same type, but there's actually different references, so not to the same thing, or false negatives in which there's the same reference, but they're typecasted, so we actually missed out on finding that same object reference. This and in fact that we cannot scan dependencies, which is done through interprocedural analysis, and the fact that there's no realistic reachability guarantees, like the NFC gadget that Alex mentioned earlier, they couldn't actually find an NFC device that actually connected to that kernel code and had to use a different syscall in order to do that. They also evaluated the mitigation through two different benchmarks versus LM-Bench, which is a more general benchmark, which is a system call benchmark for security and Linux, which allows us to measure the kernel execution speed and allows for comparison between different mitigation overhead solutions. And the reason they chose this is because it includes parallel benchmarks that use synchronization primitives compared to other single-threaded ones like Spec 2017. Micro benchmark is their way of their specifically made benchmark that stress tests synchronization primitives in the benchmark. It has a kernel. It works by having a kernel module that measures the time it takes to run n k threads simultaneously distributed across all cores, where each k thread acquires and releases the same synchronization primitive for 1 million iterations. Looking at this mitigation overhead, after running 30 independent runs for both of these benchmarks, we can see that as we increase the number of k threads, the mitigation overhead decreases. This shows us that overall, looking at both of these benchmarks, the mitigation overhead primarily occurs in very synchronization-heavy scenarios, and shows that with enough lock intention, that this overhead is actually masked very well.
So here's a slide about results and insights. We've kind of talked about these results previously, so you can just read them. In terms of the insights that we get from these results, so the first one is that no architecturally race-free code, what was assumed to be race-free code, is truly race-free because it is subject to speculative race conditions. So this gives us a new attack surface to launch all kinds of memory leaks. Right now they focus on squaff attacks because use after free attacks are some of the most common, but this is basically a new attack surface for people to be able to build new attacks on. So synchronization primitives alone are insufficient because they can be speculatively bypassed. And SRCs affect all major OSs and CPU vendors. As long as the CPU uses branch prediction and an OS uses conditional checks for their synchronization primitives, this is going to be an issue. So there's an urgent need for hardware and software fixes across the industry.
And like Alex mentioned, this paper can definitely be improved by expanding and having the detection and examination of more SRCs instead of just squaffs. And this can be done with speculative vulnerability fudgers that have a concurrent setting. This also mainly relies on the fact of branch misprediction, which is done in the hardware side, but these if statement guards are also mainly done through side channel, through a software side, since this code pattern is very prevalent there as well. And we can also further improve this with the mitigation, overhead through these newer fence implementations like the cache fence that I mentioned earlier, and more context-aware and dynamic fencing work. And like Alex already mentioned as well, they disclosed this SRC to major hardware vendors in the Linux kernel, and the Sen hypervisor actually patched this, but disabled it by default, highlighting the challenges between managing performance and security. And it would also be nice to hear a response to what AMD said, that the existing Spectre V1 mitigations already actually apply to this attack, since it relies on misprediction. The IPI storming issue that we also mentioned earlier has been patched with a rate limiting feature. However, there is concern that just limiting the rate is not enough to stop this attack.
So here's some discussion points. The first one is beyond squaff, what new classes of SRCs could exist, and how can future tools help us discover them?
Yes.
I guess probably the most obvious lead point from you have is like just a double freeze sort of thing. Basically, if you can get arbitrary rate, by having, two threads do something very similar, you can do freeze twice.
Yep, exactly. Yeah. Basically the authors also noted that like almost any of these things where we have a guard is essentially able to be a gadget in and of itself. So exactly, you're right. All these things can eventually potentially be a gadget that exposes it ultimately.
The second point is, how would architectures that allow speculative writes visible to other threads change the SRC threat landscape? The third one is, how should SRC mitigations be adapted to other architectures, like ARM and RISC-V, and operating systems beyond Linux? Because right now they focus mostly on x86 and the Linux kernel in this paper.
That's the vulnerability would be identical, just the bias is different. So that might not apply.
Yeah, so trying to like find equivalent instructions in the ISAs of these other CPU vendors, yeah.
Yep, like using a similar Cochinelle script, but specifically for these ISAs would work, something like that. Right. Thanks everyone for listening to our presentation.
Thank you, guys.
T4. Wait, 4.4.
Yeah. So one more presentation too? Yeah.
Are you Grish? Maybe you're on the Zoom already.
Yeah, I'm already on the. I already informed on it that my teammate has dropped the ball.
Got it. Okay. Okay. Sounds good. Wait, do you need me to say anything, or did you already tell him that your teammate dropped?
No, I've already made.
You've already told him. Okay, sounds good. Right. So you can prepare. That's the last one.
So my, like, is my video getting recorded?
We're recording through here.
Hi everyone, I'm Rudresh and I'll be presenting about how we use payload architecture, which is presented in this paper, to mitigate the execution overhead that we get during the speculative load execution. So this is how we'll be framing the presentation. So first I'll give the introduction of the terms that have been used in the paper, and then we'll move to a problem statement. Then we'll discuss the ideas, common ideas that we generally employ while mitigating the speculative execution architecture, and then we'll discuss the result, and then we'll go on to the conclusion. So starting with the introduction, first I'll introduce the term transmitters. So any instructions which can leak information to the attackers are called as transmitters, and it could be anything like the floating point instructions, because like for it, the latency for floating point instruction is different for different operands. And then we have the ALU instructions. So for ALU instructions, it can reveal the information that which functional unit is being used by which instructions. And then we have the load instructions, which is the most commonly attacked kind of instruction, because it reveals the memory data, because it brings memory into different hierarchies of the memory architecture. And then there's something called speculative execution, which everyone must be knowing. So it's like any execution that is vulnerable to pipeline squashes. It like the branch prediction will come under it, because if the branch evaluates to false, then whatever execution we have already run must be squashed. And then there is memory dependency execution, and in out of order execution we have something called exceptions. So if some exceptions come at certain point of in the program, then all the instructions beyond that exception has to be squashed. So all of these come from the speculative execution. Now, there is something called visibility point. So visibility point is for any transmitter instructions which can reveal information which is running as a speculative execution. So visibility point is the point for that instruction after which it is safeguarded from any attack. So basically, it is immune from pipeline squashes. So, and this is determined by the threat model, like what will be the visibility point for an instruction. So for example, let's say the branch, like for the branch prediction. So let's say we are executing a branch instruction. So once the branch data, like the branch outcome is revealed, after that, the instructions beyond that branch won't be squashed. So the branch output will be the visibility point for any branch prediction. And similarly, there are different kinds of threat models which sets different visibility points for different kinds of instructions. So in this paper, we'll be discussing about the comprehensive threat model, which more or less includes all kinds of visibility, all kinds of attacks that the load instructions are prone to. So for any load instructions to reach its VP, it has to qualify these 4 conditions. So all the branches that are older than the load instructions should be resolved. So there are no branch mispredictions. Then neither L nor any of the older instructions can suffer exception. So it should be prone to exceptions also. And then the load should not be aliased with any other older loads. And then the load should not cause any memory consistency violation. Memory consistency violation is basically when a load is running and the data that it has fetched becomes tainted in the sense that it becomes stale because some other store has overwritten the value that the load is reading. So these kind of problems come from the memory inconsistency. So it should be prone to any such violations. Now how do we decide whether a memory inconsistency has happened? For this, we have different models to determine the memory inconsistency. One of the model is total store order, which basically sets some guidelines as what all
load and store operations are possible. So basically it restricts all kind of reordering between load and store except for the store load reordering, which is allowed. But then in that particular case, it sees whether a load which has fetched a cache line, but if that cache line has been invalidated or evicted from the cache before the load has retired, then it will just squash that load and it will just undo all the instructions that has been happened after the load. So this is the threat model that we are using in this particular paper. Okay, so having understood this, the introduction part of it, I'll just clarify the problem statement. So the idea is that speculative executions are leaky because the execution is happening apart from the watch of the program control logic. So, and in that speculative execution, there are a lot of instructions, but the load instructions is the one which is more prone to attacks. Now, these load instructions are safe to execute once they reach their visibility point, which is the definition of the visibility points. Now, how do certain architectures ensure that? One way is to ensure that the load has reached its visibility points. After that, we are executing is to stall the instruction till all of these branch misprediction or exceptions and all of those things are handled, and then we execute the load, or we execute something in invisible mode, which is defined in this paper that I've referenced. So basically, what they do is that they doesn't change the microarchitectural registers, or they try to give as less information about the execution of the load. That's why it's called invisible mode. But the problem with this is that once the visibility point is reached, the instruction has to be fetched again and certain other operations need to be performed. So basically, all of this leads to some performance cost. So if we want to make our architecture safe for speculative execution, we need to either stall it or add some invisibility mode, and that has some additional performance cost. So the idea is that if we can reduce the performance cost for such secure architectures. Now, these are the four conditions that we mentioned in the comprehensive threat model. So these are the four conditions. First one is the memory consistency violation, then there are exceptions, then there is alias dependency, and then control dependency. So as you can see, like these are the different workloads. So if you can see here, the one that contributes to the most delay of the VP is the MCV, which is the memory consistency violation. So that is the primary focus of this paper, is that if we can reduce this shaded portion of the graph, so that we can reduce the time of the overhead in the execution. So how to do that? The idea is simple, is that to try to reach the visibility point for each load transmitter as early as possible. So if we can reach the visibility earlier, then the instruction is safe to execute, and then we can execute it faster. In other words, we have to make the load invulnerable to memory inconsistencies as soon as possible. Now, as I've discussed here in the previous, that this TSO, total store order, defines that any inconsistency will happen only when the cache is invalidated or evicted. So basically, we have to make sure that the cache line of the load can't be invalidated until the load retires, or the cache line should not be evicted. These are, if we can ensure these two conditions, then we can mark the loads as reached is visibility point, and then we can improve on the performance of the architecture. So the whole idea of this paper is how we can do these two things. So let's consider the first one, like how we can prevent the load from getting invalidated. So invalidation is basically a concept of the cache coherence, in which every core has their own copy of the cache, and they share the data among different caches of the core. And if one of the core writes into one of the memory location, so all the caches which stores that memory location has to invalidate their readings and has to fetch again. So that's the concept of invalidation. So we need to change the cache coherence policy if we want to delay the invalidation of the load that is pinned basically. So this is the conventional model. So how it happens is, the core 2, as soon as the core 2 gets a write instruction, it sends a getX getx command to the directory. The directory is basically something that is maintaining the communication between the two cores. So once the directory gets the getx command, it will send the invalidation request to the core one. The core one will acknowledge it, and once the core one sends the acknowledgement to the core two, the core two will unblock or release the directory for other writes to happen. So in this case, the invalidation takes place. But basically, we have to prevent this invalidation to happen as long as the load has not retired. So how do we do it? It is very simple. When the core one receives the invalidation request, it will just defer it. It will just deny to invalidate the cache line, which is for which the load is already pinned in the reorder buffer. And then the core two has to abort the write. But this definitely comes at a cost, and this is not free. So the issue is that this writing, since it has been deferred and denied to write, but it has to eventually write at some point, and it might happen that the same cache line has been blocked by different loads, and the write might never happen because it is always blocked, and this core one will keep deferring the writes. So to handle this particular problem, they have introduced a cannot pin table. So when the next time this core 2 is going to initiate the write, so instead of sending the getx instruction, it will send the getx star, which is a different instruction indicating that this is the second time it is requesting for the write. And in that case, once the directory receives the getx star instruction, it will send a invalidate star, which indicates that this is the second time to core one, that this is the second time that we are giving this request. At that instance, the core one will still defer it, because at any cost we cannot let the cache line to invalidate. So the core one has to keep invalidating all the requests for that particular cache stream. But what it will do, it will update the cannot pin table with that particular cache line. So it will prevent any further loads to reserve that particular slot. So once this load gets retired, this particular write can happen. So it will just prevent the younger loads from blocking that same line of the cache. And when there will be a successful retry, then in that case, the core one will send the acknowledgement, and then the core two will unblock it. And at the same time, this X will be removed from it, so that that particular cache line can be used again. One other problem with this particular architecture is that the CPT can also get split. So if like multiple cache lines, let's say we have only 2 entries here, and if we have multiple requests for writing, and if the CPT gets full, then again the starvation will start happening at the core 2. So to mitigate this one, they have added a FIFO queue as well. So this FIFO queue will input the core 2 request, indicating the CPT that when next time the CPT gets empty, it will reserve that slot for core 2 request, so that core 2 request can go forward, which will prevent core 2 from starvation. But obviously, it is delaying the performance of core 2. Okay, so the other issue with delaying the invalidation is that ensuring enough write buffer entries. So this is the scenario in which a deadlock can happen. So basically, both the cores are trying to execute a store, and they all have a load, but both the loads can itself not happen because of the stores that are already there in the write buffer. So we have to clear the write buffer for these two stores to happen, and when any of these stores happen, then only the load can happen. So this is a deadlock situation. So to mitigate this deadlock situation, so before pinning any particular load, it will count the number of yet to complete stores older than the load. And if that count is higher than the number of write buffer entries, then the load won't be pinned. So this is to ensure that we have enough space in the write buffer entries. So this was the first idea. This is how they have ensured that.
Also, we're running a little bit short on time, so do you want to maybe skip through like the evaluations and maybe like a discussion?
Yeah. Okay. So the other one is just to prevent eviction from the pin loads, in which case they are just denying the cache eviction. Once an eviction request comes, they'll just deny it and wait for the load to get complete for it to move forward. And then they have introduced late pinning and early pinning, 2 different variations of the pinning mechanism. So coming to the result portion of it. So this is how they have compared it on the spec 17 benchmark. and these are the parallel benchmarks on which it is comparing. So if you can see one important thing here is that if you see for this particular workload, so the late pinning is as worse as the normal without any implementations. This is because the cache misses for the late pinning will make it worse in performance. That's why they have introduced this early pinning. So the early pinning, if you can see, is considerably better than the late pinning approach. And okay, so coming to the discussion portion. So there is other works who have done the exact same analysis in which they have delayed the memory consistency thing, and they perform better than this work. But one advantage of this work over the others is that the pin load mechanism is simpler and safer to implement. So in no case they are compromising on the safety of the architecture. And then the other thing is that they are introducing new architectural units. So there is a hash mapping and all of those things in the form of CST for each level of memory, and that each level of memory, so as the memory hierarchy will change, they will have to change their architecture so that they can fit into the memory hierarchy, which is one of the downside of the paper. And then the scalability. So as the number of pin loads increase, the tracking and managing of the pin loads become a lot more expensive. And there will be other issues of hash collision and wraparounds, which are also not discussed in the paper. Thank you.
Thank you. That should be it for presentations today. Thank you guys for being here. Yeah. Do you have any questions that I can forward to Nutter regarding the class?
Yeah, like, what is the assignment after Friday? Is it it's only 0 or is it like a late penalty?
I don't know specifically. Does anyone else have an idea regarding this late policy?
I mean, the sign is already extended.
Yeah.
Yeah, it might be hard for them if it was from the original deadline.
Are you talking about CA2? I've been talking about the reviews.
He's not supposed to.
Yeah.
Oh, yeah, I'm talking about CA2.
I would say like if I would assume that, but like if you have some circumstance, like always email him like earlier than later.
Well, there be like popular credit, we cannot make that.
Yeah.
So if, will we have some popular credit, we cannot just write the program?
I would assume so, but does anyone else have any idea regarding these things?
I think there was supposed to be partial credit here.
Yeah.
I think there should be partial credit here like Campos.
Thank you guys.
Rating the CA is an auto director.
Let me just end this.